let's get going. We're going to start to talk about curves in order to introduce the concept of integration in the complex plane. Okay, so curves. So the reason we're going to talk about curves, one-dimensional curves, is that we're going to integrate along curves. And when I first saw this, I was a little bit puzzled, because when you learn about integration from calculus, you learn about integrating over intervals on the real line. You're doing calculus on the real line. So I expected integration in the complex plane to be integrating over the entire complex plane or open subsets of the complex plane. And then suddenly the discussion was about integrating over one-dimensional curves. And it seemed not completely natural to me, but there's a reason for this. And the reason is that what we want integration for is to apply the fundamental theorem of calculus. So the fundamental theorem of calculus is a one-dimensional idea. It's a one-dimensional concept. So brief recap. If we have in the real line some function like this, equal to f of a minus f of b minus f of a, like this. And what is it doing? It's an exactly perfect example of the yin and yang in calculus. So calculus, we introduced this more generalized form of addition, which is integration. We have the concept of differentiability that allows us to understand things on a very, very small scale, right? So we're adding up these very, very small changes, the very small differences in this generalized way to find the total net difference. That's the fundamental theorem of calculus. Yeah? And the easiest metaphor is to think about f as being position, f prime is speed. So if we integrate up these speeds, we have the total distance, well, the total net change in position. Yeah, it's a one-dimensional idea. We have these little changes going in one dimension, in this case along the real line, how much the function is changing as we go from x to x plus h, right? And this thing, this quotient is this number, right? And we're adding together all these tiny, tiny changes to find the total change, total net change. Yeah, it's a one-dimensional idea. There is a higher dimensional version of the fundamental theorem of calculus, and that's the divergence theorem, Stokes' theorem. But the fundamental theorem of calculus, where we assess change, means going along in a one-dimensional line. Okay, and we're going to want to do that in the complex plane, yeah, which means we're going to be integrating on one-dimensional lines, and we want to see how much complex value changes as you go from the start to the end. Yeah, so we start the discussion by trying to understand what we mean by curves in the complex plane. So this part is kind of a recap of what you learned in multivariable calculus, hopefully. Yeah, so we start with describing a parametrized curve. So and this is going to be a function. C goes from A to B into the complex numbers, okay? And it'll be continuous. Oops. Now, we will generally want a smooth curve. So a smooth parametrized curve. So from now on, parametrized gets abbreviated to this, is where z is differentiable on A cubed b, the derivative is continuous, and differentiability is pretty easy to understand, right? So this is just this thing, I'm going to take the limit, so it's mapping from something in the real line to the complex numbers. So we take this limit, as h goes to 0, of z of t plus h minus, z of t over h. This makes sense, right? This is a complex number. This is a complex number divided by h. If this limit exists, then we write z prime of t, and this is itself a complex number. Yeah? Nothing about this uses the field properties of the complex numbers. So I could be doing this from the interval into R2. It would look exactly the same. And then what is the meaning of this thing here? Well, it is just this little vector here, which goes along in this direction, right? So if this guy is point v of t, right? V prime of t is what happens when we move forward a little bit, minus to where we are, divided by the h, right? And we take the limit. Yeah? Cool. So it's clear that this vector, when I say vector, I mean identifying complex numbers as members in R2. It's clear that this thing here is pointing along the direction of the curve if it's smooth, yeah? Tell me about the length of this vector. Yeah, so the length of this vector depends on how fast our parameterization is going across this set of points, right? So this thing here could be the image of z over some interval ab, right? And we can create another curve that will go exactly across the same set of points, right? In which case, when we take the derivative of that curve, it'll still be exactly tangent to this one-dimensional curve in the plane, yeah? However, we could have a completely different speed in which we go along these points, yeah? Yeah? So z prime of t is the speed as we travel along this set of points, right? Yeah. So this is a kind of a hint that the parameterized curve and the actual set of points in the plane that we think of as a curve, that's what we naturally mean by a curve, not exactly the same things, right? We can have different parameterized curves describing exactly the same set of points, yeah? So this is something we're going to have to face shortly. Yeah? But just to the mechanics of it, just the formalities of it, this is what we mean by a derivative. This is its geometrical meaning. And we often want to have that there is some half one-sided derivative at the endpoints, because we're going to deal with closed intervals and we're going to stitch them together to have piecewise smooth curves. So you often want the one-sided derivatives to exist. And like this, a prime of a. So if we're doing a, then we can only, so this thing doesn't require any sign on h, it's just h goes to 0 in any way. But if we are here at the endpoint, then we can only move forward. So then this is the limit as h goes to 0 from the right-hand side from positive numbers like this. Okay. So it's one-sided because we're only going for positive numbers. And z prime of b, maybe I should put a quotation mark because it's not strictly a derivative. I don't know, like this. And I like to write it like this. So let's again take h going to 0 from above, but now I want to write it like this. So this we are b, and we're going to, so it's going to be z of b minus z of b minus h over h. And that thing is the same as, this is also the same as this. It's the same as the limit as h goes to 0 minus of z of b plus h minus z of b. But I prefer to write it like this. Okay, so these are one-sided limits that we want to have. So then there is some kind of a tangent here and here. Okay, so that's what we mean by a smooth parameterized curve, except we also have the condition that z prime of t is not equal to 0. No, it's okay, it's a complex number. Z prime of t is not equal to 0. What a mess. For any t inside the open interval a, b. Well, actually, since we defined this, we can do it anywhere. Like this. So that's what we call a smooth parameterized curve. Cool. All right, so as I was kind of alluding to, the set of points in the plane which we think of as the curve and the parameterized curve are not the same things, right? So we think of the actual image of this thing as being the curve. Okay, and we want to formalize that in some way, and the natural way is as follows. So if we have some other function, say w from CD into the complex plane, such that the image is the same as this guy, okay, then we'd like to have them be the same in a more precise way. We'd like to say that they are really equivalent, and we will do this in the language math as follows. We say W is equivalent to Z if and only if there exists a bijection let's call it S from A to B into C to D, running out of space, where we can go from one to the other via this bijection. So we have that Z of T is equal to W of S of T, and S prime of T is bigger than 0 for our T between A and B. Okay, that thing is what we use to say that these two curves are equivalent. Okay, so as I raise the board, look at this S of T. Tell me about what the graph of S of T looks like. So this is our condition that, so we have that S goes from A to B into C to D, where S is a bijection, and S prime of T is bigger than 0, and put it over here, I guess, and Z of T equals W of S of T, like this. Okay. So what is this thing doing? This thing is reparametrizing the interval AB, right? to the interval CD. So this condition in particular implies that, let's call this thing star, implies that the images of both those things are exactly the same, right? Z of the interval AB is the same as W of the interval CD. So the set of points that are described by this are identical, yeah? But the S itself is reparametrizing the interval AB, so this would be AB, to the interval CD, okay? And you can think about this as a kind of rescaling of time. So a nice metaphor to think about functions from the interval into the complex numbers or into the plane is to think about it as the motion of a flying bee with respect to time, right? So you can think about as t goes to z of t is the position of the bee at time t. So if we start here at z of a, then we move along, and we end up here at z of b. Yeah? That's how we can think about a function from an interval into the complex numbers. And what this thing is saying is that we start at the same, let me change color. We start at the same place, W of C, and this is W of D, okay? And for every time between A and B, it is stretched or shrunk to some time along here in a bijective way. So for example, from here to here could be stretched from here to here, but then from here to here could be shrunk from here to here, right? Yeah? All that stuff is fine, yeah? So it doesn't have to be in any way a regular rescaling of time, it just has to be bijective, yeah? So if we're going to do a graph of this thing, what would it look like? S to B, so this is A to B, and this is C to D, say. Then it is an increasing function. We know it's increasing just because it's got to be bijective. If it wasn't increasing, then it wouldn't be bijective, and this would change things completely, because we just want to rescale time with respect to this function S. It's better to use a different color. However, to be bijective, we don't need that S prime is strictly bigger than 0 everywhere. But we add this condition just because it makes things nicer. Okay. So this is what S is doing. This is our function S. Okay, good. And yeah, just think about this as a rescaling of time. So imagine putting a tape measure here. Imagine putting a tape measure here with your like 1 inch, 2 inch, 3 inch, whatever. And then the tape measure is just messed around with. So we're going to stretch some parts of the tape measure and we're going to shrink some parts. And then we have like this happening, perhaps. Something like this. We can stretch and shrink it however we want. Yeah? That is all that this function S is doing. It's rescaling things, rescaling time. However, this is useful because now it allows us to divorce the concept of the curve from the actual parameterization. Because what we're actually interested in is this one-dimensional curve in the plane rather than the parameterization. Yeah? So we can, in the language of math, define what a curve is. So we say a curve. Firstly, we say that, well, I think we've already said, we say that two parameterizations are equivalent if there exists such an S. Let me repeat that. We say that W and Z are equivalent. Okay, and we say, and we define a curve to be the equivalence class of all equivalent parameterizations to some particular choice of parameterization. So our particular choice that we started with Z is just one particular, it's like the representative of the equivalence class. Yeah? So that is maybe seems somewhat of a cumbersome definition for this concept of a curve, which seems rather natural to us. However, it is at least a clear one, or one that makes sense to us, and that's what we call a curve. So I'm not going to make a kind of big deal about this from now on. All we can take away is that whenever we have a curve in the plane, we can choose whatever parameterization we want, and that one will be fine for us. Okay, and everything I'm going to do, if it makes sense, will be independent of our parameterization. But to actually calculate things, we're going to need to use a parameterization, but I claim everything which we do going forward won't depend on it. Okay? Cool. So, another thing to say, finally, is that there is inside this an implicit orientation. Because on the real line, we make the convention that A is less than B. I mean, maybe not we make the convention, but we agree that A is less than B. So this thing here, Z of A, we think of as the start. And Z of B, we think of as the end. Yeah? So every curve has an implicit orientation. Yeah? There is some choice of the start endpoint and some choice of the end endpoint. And for every equivalent parameterization, the start endpoint is the same and the end endpoint is the same. Yeah? Cool. Okay, cool. So that's what we mean by curves. And let's do a little bit more algebra of curves and do some examples of curves. So this leads us to the concept of having a curve with the opposite orientation. So we will denote a curve by this thing, gamma, okay? And we define gamma minus. Informally, gamma minus is the curve which has its endpoints flipped. So the start point of gamma will become the endpoint of gamma minus, and the endpoint of gamma is the start point of gamma minus. Okay, so if this is gamma, we can think of this as having orientation going from the start to the end. Okay, and gamma minus will be a set which covers exactly the same set of points in the plane, in the complex plane, but the start and end point are reversed. And this obviously is important when we do calculus because, as I said, the point of doing this is to allow us to do the fundamental theorem of calculus. in the complex plane, and we obviously have to make a choice of start and end. And on the real line, it's trivial. The lesser number's the start, the bigger number's the end. In the complex plane, there's no obvious choice. It's implicit in the curve, right? So when we have a curve, we have to make the choice of what is the start and the end. And sometimes we want to go the opposite way, right? So we'll define it like this. And then formally, how do we get to such a thing? That should be D, E. Like this. How do we get to such a thing? So how do we define such a thing? So given a parametrization of a curve, let's call it Z. Just for generality, I'm going to take Z from A to B, interval A to B, but I can always take Z to be from 0 to 1, right? Because we've now learned that we can reparameterize, and that'll give us exactly the same. Well, let me say that better. We've now learned that a curve is an equivalence class of parameterizations, of that set of points. So we could always reparameterize A, B to 0, 1. And if you want, in your homeworks, whatever, you can always take 0, 1 because for obvious reasons, 0, 1 can be mapped to A, B with a mapping S that is differentiable, monotonic, and all the properties that we need. So we say this guy over here, or say this guy is a parameterization. So maybe just to emphasize this, I'm going to write, no, I won't, I just write complex numbers. So that this guy is a parameterization. We define let's call it Z minus, like this. Again, from A to B, like this, as Z of A plus B minus T, okay? So this is a definition, and let's see what Z minus does. So Z minus of B, when you put B inside this, we're just going to get Z of A, and Z minus of A, we put A into this, we're just going to get B, or Z of B. So this guy is exactly reversing the orientation, right? So this guy is starting where our Z ended, and it is ending where our Z started, right? Do you see what I mean? Nod your head if you're with me. Now give me actually a thumbs up because it's hard to see head movement. All right, good. So this guy is a parameterization over the same set of points, but now the orientation is reversed. And gamma minus is the family of equivalent parameterizations to Z minus. I should say equivalence class, but family, same thing. To Z minus like this. Okay, so we have a notion of a curve and then the negative curve, the opposite orientation curve. Okay, some examples. Or at least one example. So if we take the boundary of a ball of radius r around some complex number z0, okay? This is clearly a one-dimensional set of points in the plane. Yeah? All right, now we're going to try and come up with a parameterization of it. Yeah? So, give me a suggestion how we're going to parameterize this. We want a function from some interval, doesn't matter which one, that goes over this set of points. Z0 plus r times e to the I t, good. And then what range of t? Yeah. So we can define z of t to be this thing for this interval. Okay? And that thing exactly does what we want, right? Because we know that this guy is just e to the it as we range from t from 0 to 2 pi. It just goes around the unit circle. Yeah? That's what we learned. Yeah? So this thing is exactly, let's just draw a picture just to nail it down. So e to the it starts here. When t is 0, we're right here. And we go anti-clockwise around. This is what e to the it does. Right? T goes to e to the it. Yeah? So if we have some arbitrary point z here, z0, and then some arbitrary radius r, all we need to do to turn this parameterization into something that parameterizes this is we need to take this guy and add z0 and then multiply it by r, and then it exactly does what we want. Yeah? That's a parameterization. Yeah? So it's often not too hard to come up with parameterizations for the kind of thing that we want, and we'll be integrating around the circle many, many times. That is a guy that we'll use lots of times. Okay, this is also an example of a closed curve. So we say gamma is closed. So from now on, when I say gamma, I'm going to start talking about a parameterization that is one of the parameterizations in its equivalence class. So if z of A equals z of B, okay? In other words, we end where we start. Yeah, that's a closed curve. So this guy is a closed curve. And we say gamma is simple if it has no self-intersections. And geometrically, it's clear what that means, right? It means that the curve is not coming back to intersect itself, yeah? So it's not hitting itself like this. And how would we express that in the language of maths? Well, intersection. It does not self-intersect, i.e., if z of, let's call it t1 equals z of t2, this implies that t1 equals t2, right? So you think about this as the motion of the B. The only time the motion of the B is going over a point where it already was before, it's as if we have actually the same moment in time, yeah? So that's self-intersection, so just make this sense. So this self-intersects. Okay, and therefore is not a simple curve. So a simple closed curve is something which goes around, meets itself, and it never self-intersects. Yeah? Cool. All right. So now we are in a position to define integration finally. So all right, so we are going to take continuous functions on the complex plane just because you people have probably not learned Lebesgue integral necessarily yet. So you've learned Riemann integration, and you don't know that you can integrate this quite wide class of functions. And in complex analysis, all our functions are really nice. So we're just going to take f to be continuous because we have much more than that coming forward, as we'll see. So that's the only reason, just to make this a little bit, just to prevent you spending brain energy wondering if this actually makes sense. For sure, you know that integrating continuous function on the real line makes sense, and that's all we need for this going forward. So we take some f from some open set inside the complex plane into the complex plane, and we want to have a notion of integrating it along the curve, okay? So we want to define integral over the curve like this. We write this, and this has to have some meaning, right? We have to define this in some way, and the way we're going to do this is like this. We're going to integrate over one of the parametrizations of this equivalence class of parametrizations, f of z of t, z prime of t, dt. Okay, let's look at this for a second. Firstly, does it make sense as a formal expression? Well, yes, it does. I mean, z prime of t is a complex number. Yeah? F of z of t is a complex number. We're just multiplying complex numbers. So this thing is a complex number for every t, and then we are now doing the real integral with respect to t, yeah? Which is like a generalized summation over all these complex numbers, each one defined for t. Yeah? So this thing is itself a complex number, it's well-defined, or this is consistent, well-defined thing. Yeah? Cool. So it's a meaningful thing. It's a meaningful thing, what we've written. Yeah? But I promised you that we would do stuff that is defined in terms of curves, and curves we define to be equivalence classes of parametrizations. Yeah? So this doesn't mean anything. This is not meaningful unless it's independent of our parameterization z. Yeah? Where z is any of the parametrizations in the family gamma, or equivalently, or we can just think about this, or think of this as z is any parameterization of this set of points in the plane where we've made a choice of a start point and an end point. Actually, let's not bother to write this, it's the same thing. So I'm being somewhat careful, following Stein, defining gamma to be this equivalence class of parameterizations. But in the real world, when we actually get going with this stuff and integrating over curves, we are just going to have some set of points, and then we'll just pick a parameterization, and we will know that this thing makes sense based on what I'm about to show you. Okay? So, only makes sense if independent of a choice of parameterization. So, given any other parameterization, this time let's say it's w from c to d into the complex plane, or any other other equivalent. Okay. There exists some s from a to b into c to d with the properties that the differentiable derivative is positive and z of t equals w of s of t, right? That's what equivalence means. And so let's see if these things are equivalent. Well, let's look. If we look at this thing over here, let's write z prime of t. Now we're going to apply the chain rule. Yeah, we're going to apply the chain rule. This guy here is just a mapping from R to R. W is a mapping from the real line to the complex numbers. But the chain rule holds. I think it's one of the exercises you did on homework, at least for composing complex functions to complex functions. And this is just a special case of this. So the chain rule tells us this is true. That's what the chain rule tells us. Yeah? So we can rewrite this guy here, star, is going to be the integral from a to b of f of, let's write this guy, w of s of t, like this. Z prime we have like this, w prime of s of t, s prime of t, dt. And now we can just change variables. So let r be s of t. So dr by dt, this is just one-dimensional change of variables, is s prime of t. And then we can rewrite this in terms of variable r. Yeah? If we do that, what happens? So can you still just about see this line here? Yeah? Okay. All right. So we're going to change the limits. The limits now in terms of t, right? So when t equals a, we're going to have r of a, right? R of a. Sorry, not R of a. We're going to have s of a. And we are going to have s of b up here. These are our limits. And now this thing becomes f of w. And now r. Now this is w prime of r. And now this is dr. Yeah? And s of a is just equal to c, right? And s of b is equal to d, because s is a reparametrization from a to b to c to d, right? So this is actually just equal to c, and this is equal to d. Yeah? So what we exactly have is the same thing. Yeah? We have the same thing. Yeah? Cool. And you might be a little bit suspicious because you're thinking, okay, well, in this step right here, this is a whole jumble of things because this is a real number, this is a complex number, this is a complex number. I'm not so sure that he hasn't done some kind of tricky thing here, but you can just write out things in terms of the real and imaginary values, and then you'll have exactly an expression like this, okay? When you multiply everything out, put all the real parts together, plus I, an expression with something like this, and then you can apply your standard real change of variable formula, yeah? To have the real parts translate into a variable in R with these limits changed, and the imaginary parts translate into a variable with R with these limits changed, and you put everything back together. Yeah? So I'm using the fact that you know one-dimensional change of variable, yeah? And just some complex multiplication to multiply this out, yeah? And then you'll be able to deduce that this is equal to this if you have any concern about it. And it's actually a good exercise to do. Make sure that there's no kind of weird stuff which I'm just brushing under the carpet here. Check for yourself that this thing is a true identity just following from real change of variable. Yeah? And once you've done that, then you believe this, then we have that this is indeed a valid definition. Yeah? In fact, it's the only definition. It's the only reasonable way to define integrating along a complex curve. This is the natural thing. Yeah? This might look like a bit of a long, complicated looking formula, but actually it's the natural thing when we want to make sense of integrating a complex valued function along a one-dimensional curve in the complex plane. This is what it has to mean. Okay, cool. So that is what we now have, right? We have this ability to do that. And as I said, the point of this is to be able to do some calculus, in particular, use the fundamental theorem of calculus. And that's what we're going to check out when I clean the board. Okay, before we get to that, a little bit of algebra of integration on curves. Okay, first thing to say is what is the length of a complex curve? So, given curve gamma by z from A to B, the complex numbers. I'm going to write length. I'm just going to write len of gamma for length. It's the integral from A to B of z prime of t dt. And this is the same formula that you saw in multivariable calculus, right? So if we start here, z of A, and here, z of B, okay? Then if we want to have a notion of the length, then what would we do? This is how hopefully it was explained to you in multivariable calculus, that we would cut this thing up into little tiny pieces, right? Because the fundamental idea behind all these calculus formulas is that on a very small scale, where things are differentiable, it's very easy to detect the length, right? So if you have a straight line, it's easy to understand the length. It's trivial. Yeah. So if we cut things up into little pieces where they look a lot like straight lines, then we can get some estimate of the length. Yeah. And then we can add them up together. Yeah. And we can make these things as small as we like. Yeah. And actually pass to the limit. Yeah. And add them up in this sophisticated way with the integration. Yeah. And we get this thing. Yeah. Yeah. So this should seem natural to you. If we do a very brief sketch of this, then okay, let's do it. If we just say delta of x is equal to b minus a over n, and then we let x0 be a, and then xi plus 1 equal xi plus delta of x, so xn equals b, right? This kind of stuff. Then each individual piece right here from, let's say we look at this piece here, where this is z of, say, xk, and then the next guy along is z of xk plus 1. Yeah. Then by differentiability, z of xk plus 1 minus z of xk is really a lot like just z prime of xk times delta of x, right? Plus something which is way smaller than delta of x, actually delta of x squared if we take a smooth curve. So let's write it like this. This is big O delta of x squared. So order delta of x squared. Yeah? Just differentiability. Yeah? So if we want to try and estimate the length of this thing, the length of each one of these little pieces is a lot like just the length of the line segment joining these points, because it's almost a straight line because it's differentiable. So then the length is really close to just the sum from k equal to 0 to n minus 1 of z to the k plus 1 minus, not this. Z of x to the k plus 1 minus z of xk, yeah? And then this thing is really close to sum k equals 0 to infinity. This thing and the delta of x, the delta of x squared term will vanish because n is of order, n is, we already have it here, is b minus a over delta of x, right? So if we have delta of x squared times n, forget about it, it's going down to 0. So this thing is really a lot like z prime of xk, absolute value times delta of x, yeah? Yeah, and then this is just a Riemann sum. So this tends to the integral from a to b of z prime of t dt, right? Right, and all the formulas in calculus are proven in this way. This is what I call the Riemann sum machine. You take your problem, you cut up your whatever it is you're trying to do, volume, length, surface area, whatever, into little tiny pieces. On a little tiny piece, it looks a lot like when you have an affine function, where you can actually explicitly write down what the area, length, surface area, whatever of the piece is. Write down that expression, put it in a sum. You're looking at a Riemann sum past the limit, you have the general formula. So hopefully you people are all quite familiar with this. If you are, then every formula in Stewart's book is really, really natural and easy. You can just throw the book away because you know them all. And this is just one example. So this guy we believe. This is just background. Cool. So with this, we can start to prove or state some of these facts of proposition. Given functions f, g from the complex plane to the complex plane, and alpha, beta, which are just complex numbers, then we have the following things. So first statement, if we do the integral of this thing, alpha f plus beta of g, let me put the z's inside just to nail this down. dz, then that is the same as this thing. Get rid of this pen. And this thing just follows just by the definition, just because we know this is true for real integrals. So this guy is fairly straightforward. Actually, I'll probably ask this for homework, so you write it out for yourself and convince yourself this one's true. We have this guy is a little bit more subtle. If we do this guy, if we take our curve and do the reverse orientation curve, that's the same as minus this curve like this, which is what you'd expect, right? That's what would happen on the real line. And the whole concept wouldn't make sense unless something like this holds true. Yeah, this we will show. And the final thing, this is something we'll use fairly often. If we integrate over a complex curve like this, and we take the absolute value, then this thing is less than the supremum over our curve of f times the length of the curve. This will prove too, but it's pretty easy. Okay, so we have these basic algebra of complex integrals, and this mirrors what we would do if we were doing integrals on the real line. These are natural properties, huh? And yeah, let's just prove 2 and 3. So proof of 2. Let's do 2. So let z of t, let's just write z, be the parametrization or a parametrization. of gamma, then what do we know? Then z minus of t, which is defined by this, z of a plus b minus t, is the parametrization of z minus, right? Sorry, gamma minus. So gamma minus of f of z dz equals the integral from a to b of f of z minus of t z minus prime of t dt. Let's look at what z minus prime is. Z minus prime of t, so this is a bit unfortunate notation, is if we differentiate through this, it's going to be z prime with a minus sign here, a plus b minus t, just by the chain rule. Yeah? So let's put in what that is. So that's going to be the integral a to b of f of z of a plus b minus t, and we'll put a minus sign carrying it through, then we have z prime of a plus b minus t dt. Yeah? And now let's do a change of variable, running out of space. Let's do a change of variable, so let s equal a plus b minus t, so ds equals minus dt, yeah? And then let's change this whole thing into an integral with respect to s, right? So now when t is equal to a, s is equal to b, so we're going to integral from b, we still have the minus sign, to a. We have the minus sign, yeah? But we also have another minus sign when we go from dt to ds. So those minus signs cancel. So then we're going to have f of z of s, z prime of s ds. And now we put the integral the right way around. A is the smaller number. So then this is minus the integral from a to b of f of z of s, z prime of s. You might have difficulty seeing this in the edge, but I guess you know what I'm writing. Yeah, which is exactly saying what we want. So sorry that you probably can't see this too easily, but now I'm just going to write this thing as minus the integral gamma f dz, because that's what we have. Okay, so we've exactly established that this guy is minus this guy, just exactly this statement. Yeah? And all we've done is just put in the definition of what the inverse curve is. We take our parametrization, send it going the opposite way. Yeah? Put that in, just work it out, work through the consequences, and it just falls into our lap. Yeah? So this guy is true. Let's also quickly kind of sketch this one. Let's try and squeeze it onto one board. Let's try and do this guy. Sorry, this guy, I. Okay, we're going to directly put in the parameterization straight away. So we have the integral from a to b of f of z of t, z prime of t, dt. That's just the definition of the integral. We put the absolute value signs through inside, which we can do because this thing is just the integral of a complex valued function from the real line. So as a real and imaginary part, just put the absolute value signs directly inside. And then this thing is less than equal to the integral from a to b of the absolute value of f of z of t, z prime of t, dt, and then this thing is less than its supremum over the curve. So then this is less than supremum over the curve of f, integral from a to b, z prime of t, dt, and we've just recapped that this thing is the correct formula for the length. So this thing is the supremum of f over the curve times the length of the curve gamma. And that's what we want, and that's what we expect, and that's what's true. Yeah? So that is this formula here. Yeah? So these basic properties of complex line integrals, complex curve integrals, what we just call complex integrals actually going forward, because these are the kinds we're going to be doing all the time. These follow easily. Yeah? Everybody happy before I erase the board? Yeah? Cool. All right. Okay, so we have the big reveal, which is that we have the fundamental theorem of calculus holds true in the complex plane when we integrate across curves, right? But fundamental theorem of calculus, obviously we need a notion of a primitive, right? So we say that capital F from some subset of the complex numbers, we're always going to take open subsets, is the primitive of little f from the same set, just in the obvious thing you might expect, if and only if the complex derivative equals this, all z belonging to omega. Yeah. So we have this notion of complex derivative, which exists at every single point of the complex plane. It's well defined. It's an individual complex number. So this thing makes sense. Yeah. This thing makes sense. Yeah. Yeah. And that's one of the interesting and weird things. This is now in 2 dimensions. We now have this 2-dimensional field. We have this 2-dimensional derivative for 2-dimensional valued functions, and we have exactly the notion of primitive. Yeah? Yeah? So normally, when we take the derivative of things in multi-dimensions, it's a complicated object. Right? We take the derivative of a 1-dimensional curve into R2, it's a vector, right? Yeah. We take the derivative of a function from R2 to R2, it's a matrix, right? There needs to be more information in the derivative as we take more and more complicated things, as we take higher dimensional things. What is cool and interesting and makes this thing so powerful is that in this case, because we have a field, a 2-dimensional field, the derivative is a complex number, just like everything else in this game. Yeah? So we have this natural notion of derivative in this 2-dimensional field. Yeah? Yeah? Cool. Yeah? But we are going to be doing integration on 1-dimensional curves because the fundamental theorem again is a 1-dimensional concept. Yeah? So we have fundamental theorem of calculus in the complex numbers. Theorem. Suppose f is the primitive to little f as above, and gamma is contained within, or is a curve inside, let's write it in words, with endpoints, with start point, let's say Z1, and endpoint Z2, because as we know, the curve has inside its definition a start point and an endpoint. Then, if we integrate over this curve, f of z dz, it is equal to capital F of endpoint z2 minus the start point z1, exactly as the fundamental theorem of calculus on the real line. Okay? Okay. Proof. Take a parametrization. Then, what does this mean? Then integral of gamma f of z dz is the integral from a to b f of z of t z prime of t dt. Yeah. And what is this? This is the same as doing this. Integrate from a to b of d by dt of capital F of z of t like this. Because by the chain rule, d by dt of capital F of z of t equals this thing, the complex derivative, times this thing. Yeah. Another example of doing the chain rule. Again, I think this was what I set you for last homework, right? Or at least the first homework. Yeah. So this is something you should be happy with. Yeah? So this is true, and by definition, this is f of z of t, z prime of t, because the complex derivative of capital F is exactly this guy. Yeah? So this step is true. Yeah? And then, therefore, gamma of f, this thing, is exactly what we want to, exactly this expression here, which we can evaluate just using the fundamental theorem of calculus itself. Yeah? So this is equal to capital F of z of b minus capital F of z of a. And you might be slightly concerned. You're thinking, okay, but he's using fundamental theorem of calculus, but this thing, f of z of t, is a complex valued function from the interval a, b into the complex numbers. True. But again, if you're in any doubt about this, just write out the real and imaginary components of f, and convince yourself that from going from here to here, all I'm doing is doing the fundamental theorem of calculus on each part, the real and imaginary part. Write out the algebra of the complex number algebra to convince yourself that this is true. Okay? And then this is just our statement. This is exactly our statement. So this is f of this guy minus f of this guy. And that's it. So we have a notion of integrating on curves, which is well defined. It's defined on the curve itself, independent of the parameterization. It's meaningful on the curve itself. And we have a fundamental theorem along the curve. We can integrate these small differences along the curve and have the total net difference, yeah? Which is exactly the fundamental theorem of calculus. Yeah? And then this is going to allow us to start to develop calculus from the complex numbers to the complex numbers, and we'll see how very different a story this gets to be. Okay, cool. So this is where the subject starts to really kick in. All right, everybody happy? Yeah? So have a great day and see you on Thursday. Bye-bye.